So now we're getting close to the end of chapter 6. So now we get to solve rational equations. So again, just a bit of a definition. You can tell something is a rational equation because it's an equation, meaning there's an equal sign, that contains at least one rational expression, meaning there's a variable in the denominator. So if you have an equation that has a variable in the denominator, you know that it's a rational equation versus a quadratic equation versus a linear equation. Anytime you're solving a rational equation, you have to be careful with your domain. Your domain of a rational equation is restricted because your denominator can't equal 0. When we did 6.1, we looked at the denominator or the domains of rational expressions, and we just had one expression, whereas a rational equation could have a number of rational expressions or rational terms. So it will be the intersection, meaning all of the domains of all the rational expressions combined together. The other thing to be careful with is the fact that because there's restrictions in my domain, when you solve a rational equation, we say that we get proposed solutions, meaning just because you've solved it doesn't mean it's going to be a solution. So all the solutions to a rational equation are proposed, and any solution that makes the denominator equal to 0, in other words, matches your domain, has to be discarded. Okay? So let's look at our steps. When we solve rational equations, my first step is to determine the lowest common denominator. Actually, I should put in a step 0 here. My first step is to factor. I'm going to put that into these notes. So step number 1 is factor. And then step number 2 is going to be to determine the lowest common denominator and the domain of your rational equation. So it'll be the intersection of all of the domains of the expressions. Then we're going to multiply each side of the equation by the lowest common denominator, just like we did in chapter 1. If you're someone who liked creating a common denominator instead of multiplying by the lowest common denominator, that's great. It'll give you the same result. Then you'll solve the resulting equation. It will either be linear, in which case you'll solve algebraically, or it'll be quadratic, which you'll solve by factoring. And then you're going to check that each proposed solution is in the domain and discard any values that are not. So, first equation. Step number 1, factor. Well, there's nothing to factor. So we're going to move on to step number 2, which is step number 1 here, which is to determine the lowest common denominator. So I have a denominator of x, I have a denominator of 2, and I have a denominator of 2x. So my lowest common denominator will be 2x. Right away, I like to determine my domain. So once you have your lowest common denominator, just find the domain of it. So 2x cannot equal 0. Divide both sides by 2, and my domain restriction will be that x cannot equal 0. So when I solve, if I get a solution of 0, I will reject it. My next step is to multiply every single term in the equation by 2x. So I'm going to take that 2x and I'm going to multiply it by 2 over x minus 2x multiplied by 3 halves is equal to 2x times 7 over 2x. Then, the whole point of doing that is to destroy the denominator. X divided by x is 1, 2 divided by 2 is 1, 2x divided by 2x is 1. I'm left with 2 times 2 minus x times 3 is equal to 7, or 1 times 7. If you were doing the creator method, right, this fraction gets multiplied by 2 over 2. This one gets multiplied by x over x, which would still leave you with the same result. Then I'm going to simplify. I'm left with 4 minus 3x is equal to 7. And then this is a linear equation that I'm going to solve algebraically. So I'm going to subtract 4, subtract 4. I end up with negative 3x is equal to 3. And then I'm going to divide both sides by negative 3. And I get x equals negative 1. Then you always want to check, is that in my restricted domain? How do I answer that? That was a weird way of wording it. Is it the restriction? No. In other words, great. Okay, so this was a proposed solution, and then I can declare it a solution because it's in my domain, not in my restricted domain. I feel like is what I was trying to get at with that. All right, next one. Step number 1, factor. So when I look at this equation, I've got 2 over x minus 3 minus 3 over x plus 3 is equal to 12 over this difference of squares, which is x minus 3, x plus 3. And these ones will always be designed kind of like when you're adding and subtracting fractions, where denominators should be somewhat similar. Now, my lowest common denominator will be the x minus 3, the x plus 3, which means that my domain is that x minus 3, x plus 3 cannot equal 0, which would tell me that x cannot equal 3 or negative 3, right? X minus 3 cannot equal 0, so x cannot equal 3. X plus 3 cannot equal 0, so x cannot equal negative 3. Now we get to solve. To solve, you're going to multiply every term by the lowest common denominator, or just create that common denominator, whatever you want. Okay, I find the textbook teaches it this way. There must be a reason. So I'm going to do it this way. If you're a creator, that's awesome. Since I multiplied everything, now I can destroy. So x minus 3, x plus 3, and then both. So what am I left with? I'm left with 2 times x plus 3 minus 3 times x minus 3 is equal to 12. Okay, a nice linear equation. So I'm going to simplify. I'm going to multiply the 2 through to get 2x plus 6. I'm going to multiply the negative 3 through to get negative 3x plus 9 is equal to 12. Then I'm going to collect like terms. I get 2x minus 3x is negative x. 6 plus 9 is 15 is equal to 12. Then I'm going to subtract 15 from each side. So I end up with negative x is equal to negative 3. And then I'm going to divide both sides by negative 1, and I get x equals 3. Last step, check it with your domain. Since x cannot equal 3, and this is my only proposed solution, that means that this question is destined to fail. There are no solutions to this problem. I had to reject my only proposed solution. You can either do an empty set bracket, or you can put your null sign. Okay, which means no matter what I put in for x, nothing will make this equation true. All right, next one. Next one looks a little bit more complicated. It's just a whole lot of factoring. So step number 1, let's factor all of these denominators. I have a 3 over, I'm looking for two numbers that multiply to give me negative 2 and add to give me positive 1. So that'll be 2 and negative 1. So I'll have p plus 2, p minus 1, minus 1 over, this is a difference of squares, so it's going to factor to p minus 1, p plus 1, is equal to 7 over, they snuck in this darn 2, and then I've got a trinomial. Two numbers that multiply to give me 2 and add to give me 3 are 2 and 1, so it'll be p plus 2, p plus 1. Whew, okay, so what is my lowest common denominator? I'm just going to get rid of that so I have some room. My lowest common denominator, I've got a p plus 2 and a p minus 1, so that has to be there. I've got a p minus 1 and a p plus 1, so the p plus 1 is taken care of, but I need a p minus 1. And then I have a 2 that I need, and then I have a p plus 2. Oh, that was supposed to be a plus 2. Whoa, I was like, really? More? I feel like I did that really weird. I'm just going to start that sentence again. If you already copied it, and hopefully you didn't do what I wrote. So let's look at our denominator again. There should be a p plus 2 and a p minus 1, right, from this first bracket. I think I put opposite signs. From this one, I need a p minus 1, which I already have, and I need a p plus 1. From this one, I need a 2, and then I need a p plus 2 that I already have, and a p plus 1 that I already have. Whew, there we go. Then I'm going to write my domain. My domain is that p cannot equal. So I'm going to take each of these parts of my domain and say that they cannot equal 0. So 2 cannot equal 0 is fine. It will never be 0. P plus 2 cannot equal 0, so p cannot equal negative 2. P minus 1 cannot equal 0, so p cannot equal 1. And then p plus 1 cannot equal 0, so p cannot equal negative 1. So my restrictions are that p cannot be negative 2, negative 1, and 1. Now to solve it, you're going to multiply every single term by that lowest common denominator. So a 2 and a p plus 2 and a p minus 1 and a p plus 1 to every single term. So with these ones, even though the denominators are kind of crazy, it will simplify, I promise. All right, and then we start destroying. So for this one, I get to get rid of the p plus 2 and the p minus 1. So the only things I need to multiply by are 2 and p plus 1. For this one, I get to get rid of the p minus 1 and the p plus 1. So I just have to multiply by the 2 and the p plus 2. And then for this one, I get rid of the 2, the p plus 2, and the p plus 1. So let's see what's left. And again, if you don't like the crossing out, this is where the creating a common denominator comes in. So this guy was missing, the 3 was missing the 2 and the p plus 1. The negative 1 was missing the 2 and the p plus 2. And then the 7 was missing just the p minus 1. So you can kind of look at your denominators and look to see what they're missing, and that is what gets written here. That's the creation method. The destruction, you actually get to physically get rid of them and see what's left. It's just a different way of seeing it. So for here, I have 6 that I'm going to multiply through. That will give me 6p plus 6. Here I have a minus 2 that I'm going to multiply through. So I'll have a minus 2p minus 4 is equal to 7p minus 7. Collecting like terms, I have 6p minus 2p is 4p. I have 6 minus 4 is 2, equal to 7p minus 7. Then I'm going to put my p's on one side. Now it doesn't matter which one. I'm going to put my p's on the right. So I'm going to minus the 4p to get my p terms on the right. I'm left with 2 equals 3p minus 7. Then I'm going to add 7 to each side to get 9 equals 3p. And then lastly, to get p by itself, I'm going to divide both sides by 3. And I end up with 3 equals p. Then I have to check up here against my proposed solutions. 3 is not one of my, I shouldn't say proposed solutions, check with my restricted domain. P is not one of my restrictions. P being 3 is not one of my restrictions, so my solution is 3. Now, for this one, I feel like I did a lot of work, and I would like to make sure that I got it right. So I'm going to check this one. To check your solution, and I checked this one because it's complicated, right? You're going to put 3 in for p. So you get 3 squared plus 3 minus 2 minus 1 over 3 squared minus 1. Does that equal 7 over 2 times 3 squared plus 3 times 3 plus 2? Okay. If I'm plugging this in to check, I'm doing it all in my calculator. So what I'm going to do is I'm going to make sure all the things that are in denominators that have an operation are in brackets. So for this first one, I'm going to type in 3 divided by bracket 3 squared plus 3 minus 2 unbracket minus 1 divided by bracket 3 squared minus 1 unbracket equals. I get 0.175. For the right-hand side, again, you're going to make sure this is in brackets. So you're going to need double brackets. So listen how I say it. I'm going to do 7 divided by bracket 2 bracket 3 squared plus 3 times 3 plus 2, close that first bracket, close that second bracket equals. And I also got 0.175. So I'm good, right? Hard question, but we persevered, we made it to the end, and we got a solution that works, which is great. This last example that we're going to do, okay, we're going to talk it through. So step number 1. Lowest common denominator. Well, sorry, step number 1, factor, but there wasn't anything to factor. So step number 2 is I'm going to find the lowest common denominator. So I need an x and I need a 3x plus 1. So then the domain would be, again, x cannot equal 0 and 3x plus 1 cannot equal 0. Now, if you're having a hard time, I felt like I was kind of not showing enough work for you there. So don't forget, you can also do 3x plus 1 cannot equal 0, and then solve it, right? Minus 1, 3x cannot equal negative 1, and then divide by 3, and you get x cannot equal negative 1/3. So those are my two domain restrictions. Now let's solve. So to solve this, I'm going to take each term and multiply it by x times 3x plus 1. So for this one, the first one, I can get rid of the 3x plus 1. I'm left with just the x. This one I can get rid of the x. I'm left with just the 3x plus 1. And this one I can get rid of the 3x plus 1, and I'm left with just an x. So I'm left with 2 times x is equal to 1 times 3x plus 1. And then minus 6x times x. Simplifying, I get 2x is equal to, multiply the 1 through, I just have 3x plus 1, minus 6x squared. This is not a linear equation. This is a quadratic equation. And the only way we know how to solve quadratic equations right now is to factor and use the zero factor property. So I'm going to put everything on one side and make it equal to 0. So I'm going to add the 6x squared. I'm going to minus the 3x, and I'm going to minus that 1. If it's too much at once, do them one at a time. But I do like minus 6x squared, or sorry, plus 6x squared, minus 3x, and then minus the 1 would leave me with 6x squared minus x minus 1. Now, some of you are probably like, why didn't you just minus 2x? I could have, but then I have a negative out front, which factoring AC with a negative out front is just awful. So because you get the choice, I would always put it on the side that gives me the positive x squared term. Then this one, to add extra chaos into the mix, it's not a 1 in front, so I have to go like that, find my AC. So I'm looking for two numbers that multiply to give me negative 6 and add to give me negative 1, so it's negative 3 and 2. And I can't just go straight to the brackets. I have to do the whole thing, and we haven't done it in a while. So 6x squared minus 3x plus 2x minus 1 equals 0. Then I'm going to factor by grouping. Out of the first group, I could take out a 3x to be left with 2x minus 1. And then out of the second group, I'm not going to take anything. It's already a 2x minus 1, so I'm going to pull out a plus 1. Then I'm going to greatest common factor out that 2x minus 1 bracket and be left with 3x plus 1 equals 0. Then to solve this, I'm using the zero factor property. So I'm looking at my two solutions being 2x minus 1 equal to 0 and 3x plus 1 equal to 0. To solve this one, I'm going to add 1 to each side. I end up with 2x equals 1, and then divide both sides by 2, and I get x equals a half. For this one, same thing. I'm going to minus 1. I get 3x equals negative 1. And then I'm going to divide by 3. And I get x equals negative 1/3. These are proposed solutions that I then have to check up against my domain restriction. Because x cannot equal negative 1/3, I'm going to reject this solution. And I'm going to say that the only solution is a half. Okay, and then if I wanted to check, I could plug it into check. That's the end of solving rational equations. I had to throw this last example in. It's the exact same terms, but I've switched the equal sign to a plus sign. Why? Because I find once we learn this lesson, which is solving rational equations, everybody's like, oh my gosh, this is great. I get to get rid of the denominators. Doesn't that make everything easy? And I'm like, except it only works when you're solving equations, right? I'm only allowed to multiply by the lowest common denominator because of this equal sign. Because of the equal sign, what I do to the left, I can also do to the right. If you go back to thinking about 6.2, when we are adding and subtracting rational expressions, I can't just multiply this by x times 3x plus 1 because there's no equal sign that I can do one same thing one side and the other. This is just an expression, and you can't just multiply an expression by whatever you want, right? So we'd be back to saying, hey, what's the lowest common denominator? X times 3x plus 1. That doesn't change. But what changes is I can't multiply every term by it. I'd have to create that common denominator. So for this guy, I'd have to multiply by x over x. For this one, I'd have to multiply by 3x plus 1 over 3x plus 1. And then this one also, I would multiply by x over x. So you can't just multiply, but you can multiply by 1, right? So I can multiply every term by 1, which will leave me with 2x over x times 3x plus 1, plus 1 times 3x plus 1, all over x times 3x plus 1, minus 6x times x, all over x times 3x plus 1. I can create that common denominator so that I can write it with the common denominator. So my denominator would be x times 3x plus 1. They all have it in common. And then my numerator would be 2x plus 3x plus 1 minus 6x squared, which would simplify to negative 6x squared plus 5x plus 1 all over x times 3x plus 1. And then once you've collected like terms, you always look to see if I could simplify my numerator. In other words, if I could make it factor so that there'd be a common factor. Oh, and this one we'd have to check. So let's check it over here. Let's go negative 6x squared plus 5x plus 1. The first thing I would do is factor out the negative 1 so that I can factor something with a positive coefficient, leading coefficient. Don't talk and write at the same time, Karen. Minus 5x minus 1. Then I'm looking to see, are there two numbers that multiply to give me negative 6 and add to give me negative 5? Yep, negative 6 and 1. So then I keep going. But notice I'm doing my factoring outside. If you try to do it within your question, you're having to write your denominator so many times that you just won't do it. So I've got the negative 1. Then I've got 6x squared minus 6x plus x minus 1. Then I'm going to factor by grouping. So out of the first group, I could take out a 6x to be left with x minus 1. And then out of the second group, I could pull out a 1 to be left with x minus 1. And then I have that common factor of x minus 1, and I'm left with 6x plus 1. So I didn't need to, right? I don't have to even include this in here. I could just say that this is the final answer if I wanted to, because just to prove that I did all the work, I could write it in factored form, but there's no point to it because nothing's simplified. So either one of these would be a perfectly great answer, but you always have to check. So big difference. This one, we got to a point where x equaled things. There was values of x that made this equation true. This is just a simplified form of the expression. All we did was create a common denominator so that we could then add and subtract the numerators. Awesome. You are done.